And this understanding leads us to molar conversion, also known as stoichiometry, a part of stoichiometry. Also, I like to call the mathematics of it dimensional analysis, because that's what it's called in other sciences. But it just means any part that you have, because you have a conversion ratio, you can go back and forth. So we can figure out, we can go from the mass in grams to the number of moles to the number of particles, or the number of particles to the number of moles to the mass in the grams. So you can move it all around. Okay, we need to take a step back for a moment here and look at basically what's called stoichiometry, or I call it dimensional analysis because it's really used in all the different sciences. When we use moles, so that 1 mole is equal to 6.02 times 10 to the 23rd molecules. So when we use that, it is essentially going to be stoichiometry, because we can do so much in chemistry relating things to their molar mass and the moles and all of that. And we've just talked about that because even the periodic table gives us things in grams per mole. And so we can go from molecules or atoms into moles, into grams, and back and forth. That's what we were talking about before. But why is the question? And really it has to do with any true equivalency, such as this right here, can be easily manipulated in order to make a rational statement that is equal to 1, okay? Let's use a different one, though, besides that one, so that I can prove my point here. For instance, we know that there are 60 seconds in 1 minute, right? And we even know another one. We know that there are 60 minutes in 1 hour. So both of those are true statements, right? Mathematically, they equal each other, even though 60 equals 1, because of the unit, both of these are true, right? It does 60 seconds is equal to 1 minute, 60 minutes is equal to 1 hour. So that means you can divide either side through in order to use it to calculate. And so we use something called the railroad track method. And that's where you have a nice little railroad track here. And you start by putting at the very top whatever you're going to be changing. So for us, let's go ahead and make it, let's say we want to know how many seconds are in 23 hours, right? Well, now that we need to use hours, we're going to use this equivalent statement right here. But whatever we put on the top, up here, we need to put that unit on the bottom. So I know that I'm going to want hours on bottom, and that's going to give me minutes on top. Why is it going to give me minutes on top? Because essentially what I'm doing in this section right here is I'm multiplying my statement by 1, because anything times 1 is itself, right? And I can prove that this equals 1, because all you have to do is a mathematical trick. If I wanted hours on bottom, then I'm going to divide both sides by the same thing. I'm going to divide it by hours. And you're allowed to do that, right? So if I divide this by 1 hour and this side by 1 hour, then hours over here cancel out and it's just equal to 1. So now I have a statement that says 1 is equal to 60 minutes divided by 1 hour. That's another true statement. As long as this statement is true, then this statement has to be true, right? And that's why we can then write that stuff in on our railroad tracks. And we can say that we have 60 minutes times 1 hour. But like I said before, we're not quite done yet because we wanted to go to seconds. And we can go ahead and see that hours are going to cancel out and we have minutes. Well, now we're going to want minutes on bottom. Let's go ahead and write that back in white. minutes on bottom, and seconds on top. Well, we can do that with this true statement, right? So if I was going to solve that around and I want minutes on bottom, I'm just going to divide both sides by minutes, and I'm basically going to get that 1 is equal to 60 seconds divided by 1 minute. That is a statement of 1. And so I can now write in 60 seconds, 1 minute, and look what happens here. Our minutes are going to cancel out, and we're going to be left with just seconds as our overall unit, or our dimension. Thus they call this dimensional analysis. Now, this also is equal to 1, so we're really just multiplying that 23 hours by 1 twice, which means we still have 23 hours, but because our units changed, we're going to end up with new units in another equivalency statement, like this, because it's going to equal that. Now, the railroad tracks method, all you have to do is everything that is on top on the railroad tracks, you multiply across. And then you go back and you divide by everything that's on the bottom. So multiply on what's on top, divide by what's on the bottom. So luckily, if we divide by 1, it's going to be the same thing. So really, we just need to multiply 23 times 60 times 60. When we do that, you're going to get 82,800 seconds. And so now we can write that 23 hours is equal to 82,800 seconds. Now, I start with this because you've probably done this in your head a lot with time before. You just didn't realize you were setting it up in this manner, that this is what was going on, right? You knew that there were 60 minutes in an hour and 60 seconds in 1 minute. And so if you need to figure out how many seconds were in 23 hours, you knew you would multiply it by 60 twice. And you know that the statement's true. So you can see how all of this works and is in fact correct. I say that because we now need to go back and do this with things that are moles, okay? So now that I know how to use the railroad tracks method, I can use it to figure out a lot of things with moles, and this is that stoichiometry that comes into play. Notice my railroad tracks that are down here, and notice this type of question: how many moles of carbon are in 26 grams of carbon? Well, notice they started on the railroad tracks, they put their 26 grams of carbon, okay? They next needed an equivalency statement. Where did they get this equivalency statement? The periodic table. Because if you remember, this is the molar mass. Essentially, what it says is you would see on carbon, it would say its molar mass is 12.01 grams per mole, right? Well, that just made that statement for you pretty much, because what that really means is that 12.01 grams of carbon are equal to 1 mole of carbon. And because that's our equivalency statement, you can divide either side by itself to move it around the top or bottom, right? So even though if you look at this one and it's grams over moles, we can rewrite it as moles over grams because we know that this is true. Because of that, I set it up. I know that I have grams on top. I want to put grams on bottom. So that's going to put the 12.1 grams of carbon is equal to 1 mole of carbon. The grams of carbon can cancel out. I'm going to divide because 12 is on the bottom, right? And I can multiply it by 1 if I want. But then I'm going to get 2.2 moles of carbon as my answer. And when we use this mole, it's considered stoichiometry. But really we're doing that dimensional analysis where we change the dimensions of whatever we're working with in order to find our new product. And so even when we're finding out things like how many molecules are in 2.5 moles of sucrose, basically, or glucose, sorry, not sucrose, glucose, we're going to basically just use the same thing. We put the amount that we know up top, 2.5 moles, right? And then we use Avogadro's number, which states that 1 mole is equal to 6.02 times 10 to the 23rd parts, or molecules, or particles. Molecules, okay? So when we have that equivalency statement, we can put what we need on the bottom, moles in this case, so that they cancel out. And we see that these numbers are side by side, so we multiply through. The unit that's left is molecules, and so that's what we're going to be left with. And so you get your answer again. Again, this is the same thing as if you think about doing it with time. You can go from seconds to minutes, and minutes to seconds, and seconds to hours, hours to minutes, all of it by using the same method, right? It's no different. We're just using different equivalent statements. Now, just like with the time units we were using when we went from hours to seconds, we had to make 2 different jumps, so we needed 2 equivalent statements. This one is finding the mass of 2.1 times 10 to the 24th molecules of sodium bicarbonate. And so to do that, we're going to have to first convert the moles, or the molecules, into moles, and that's Avogadro's number, right? That's that equivalency. And then luckily, if you remember our last video, we could figure out the molar mass of sodium bicarbonate by going to the periodic table and finding how many grams per mole of sodium, how many grams per mole of hydrogen, how many grams per mole of carbon, and then multiplying 3 times how many grams per mole of oxygen, and adding all those together give us another grams per mole of this one single molecule, right? Well, if we have this many molecules, we put molecules on the bottom, so we get rid of molecules. There's that many molecules per mole, so now we have moles, and then we use that it was 84.1 grams per mole, so the moles are on bottom, grams on top, moles cancel out, and we're left with grams. And so you get that it's 290 grams of sodium bicarbonate. It looks more difficult because it can actually go through a couple of stages of this. I've done some in physics where I just kept adding on here. I needed another railroad tracks and then another railroad tracks. And as long as you keep canceling out the units and following that rule where we multiply on top and we divide on bottom, then you're going to be fine with whatever your end result is. The railroad track puts it all up in proper placement for you. It's also important to remember that number. I have this nasty mole on my hand. 1 mole is equal to 6.2 times 10 to the 23rd molecules or particles, or whatever you're counting, basically. Hope that helps.